Hi everyone, I'm going to present in this slide Line, which is an engine to analyze extended and layered QE network models. These slides were presented as part of the demo session at ICPE, the International Conference on Performance Engineering in 2019. Line is a MATLAB library that allows to calculate with ease performance and reliability metrics for models such as queuing systems and QE networks, which can be dealt with either analytically or with techniques like simulation. In the past, this tool was based on a single analysis technique called fluid approximation, but since its last release, version 2, the tool has changed and now has a greater ambition as it wants to offer a variety of different methods to analyze a rich family of queuing models. You can see in this slide a screenshot of the website, which you can reach at the address shown in the slide title, which links to resources such as downloads, the manual of the tool, a wiki with details on the different algorithms and features of the tools, as well as other videos. Among the main features of Line are now an object-oriented language, which offers a rich set of constructs to describe extended and layered queuing models. In addition, the model described with this language, which is an object by itself, can be automatically translated into the different data structures and file format which are parsed by the different solution methods and algorithms integrated with Line. Several of these algorithms have been natively implemented within Line and therefore are coded using the MATLAB native language. However, there is also seamless integration with some popular tools for performance evaluation, like Java modeling tools, LQNS, and BO tools. In numbers, Line features over 40 algorithms for networks composed by over 14 types of nodes, and these nodes can interact in different ways. For example, there are multiple routing strategies for jobs between these nodes, and the nodes themselves can have different scheduling policies. There are also 13 different types of analysis that can be run on the models, and the 4 metrics are systematically supported to the tool, namely computations of utilizations, throughputs, response times, and queue length. Overall, the Line object-oriented language features over 100 different classes. One of the main ideas essential to the last version of Line is that the abstractions present in the Line language should closely resemble those available in Java modeling tools. In particular, we are seeing in this figure a screenshot of JSON Graph, the simulation environment of JMT. In Line, we have functions that allow to import models defined in JSON Graph or in other tools of JMT like JMBA automatically in Line. Vice versa, as we can see in the left part of this figure, we might define and solve a model through JMT within MATLAB. As you can see, we are invoking solver JMT and obtaining a set of performance metrics, namely queue length, utilization, response times, and throughputs at different resources of our model. There is also the possibilities, as we can see in the last line of this MATLAB screenshot, to automatically generate from MATLAB a corresponding JSON Graph model that can be sent automatically to JSON Graph, which will therefore show a graphical image of the model we have defined in MATLAB. Line features different solvers which implement different solution algorithms for the analysis of queuing models. Once we have defined with our object-oriented language a model object, which is shown here in bold, or we have imported it directly from a JSON Graph or JMBA, Several techniques can be applied to analyze this model. For example, the solver CTMC is a technique based on continuous time Markov chains in which we describe the state space of the model. The interactions between the components are described in terms of transition rates between these states, and therefore an infinitesimal generator is created for this continuous time Markov chain and solved numerically using linear algebra techniques. There are also approximations available in this solver to reduce the cost or to make the analysis feasible. The solver fluid is a technique inherited from the earlier version of Line, which analyzes a model through the so-called fluid approximation, which attempts to analyze the average behavior of the different jobs that travel through a QE network model using fluid ordinary differential equations. As shown before, solver GMT allows to solve line models through GMT, namely either through JSIM or JMVM. The mean value analysis technique, although it is available through the solver GMT, is also available within Matter through solver MVA, which differs from the JMVA solver as it supports a variety of models that are not included in JMT. For example, models with high variability or other features which are not part of the class of models that can be exactly analyzed with MVA, but they can still closely approximated based on the same theory. Matrix analytic methods are techniques that consider the continuous time Markov chain that describe the dynamic of a queuing system, and in case this Markov chain has a repetitive structure, they allow to solve it exactly, even in cases where this CTMC has an infinite state space. SolverMAM implements these techniques and also includes approximations based on these techniques to analyze a network of queues. The ANSI solver focuses on the so-called normalizing constant of closed queuing networks, which is a particular quantity available for certain kind of models to describe both average performance metrics and probabilistic measures. A rich literature exists in the scientific area of queuing network theory that studies this quantity and allows a number of approximations which are particularly effective in models with many jobs. The SSA solver, lastly, also considers the CTMC, but simulates it using the so-called stochastic simulation algorithm. In particular, differently from GMT, this model can parallelize the solution over multiple cores, therefore accelerating the analysis. However, GMT on certain models can be more flexible. For example, models that use Pareto distributions cannot be analyzed using CTMCs. These models that we have discussed so far are queuing networks that can either be so-called product form models, which can be analyzed exactly, or extended queuing networks, which introduce features that may not be analyzable in exact manners, but can be approximated efficiently. There are, however, other classes of models that are considered in GMT, such as, for example, layer queuing models, where different layers are used to represent, for example, different software layers or hardware layer in a complex IT application, which interact with each other through calls. Solver LQNS is a wrapper for the LQNS solver that sends the line model of a layered queuing network to LQNS and parses the results back into the MATLAB environment. However, Line features also its native layer queuing network solver called Solver LN, which differently from LQNS has the possibility to use a customized solver at each different layer of the model. So, for example, a layer might be solved in simulation using GMT, another layer might be solved using the NVA technique or fluid approximation. This may be helpful in certain situations, for example, where a portion of the model should consider features that are not supported by the analytical solvers. This principle of being able to use different solvers over different portions of the models is defined in line also in other parametric solvers, in particular the solver ENV, which is a solver for models immersed in random environments. To give an example of this class of models, you might consider a QE network in which, depending on the state of an external environment, which varies between state 1 and state 2, we may use a different parameterization for the model. So, for example, one of the Qs may become faster in one state and slower in the other state. These kind of models can be analyzed in an approximate way using a solver ENV. There are several demos available to the wiki and the manual that illustrate the practical use of Line on a different and diverse set of models, like models of queuing systems, like the MM1 or the MG1Q, closed models, as those arising in the machine interference problem. We also have examples that relate to load balancing, two reentrant lines used in manufacturing. Line is one of the few tools that are available to analyze caching models, and in particular it supports uniquely the possibility to add these caching nodes to a queuing network model and condition the behavior of the jobs that circulate in these networks on whether they had a cache hit or cache miss in the cache nodes. These nodes can be parameterized with different replacement policies like round robin, LRU, or others. There is also native support to analyze response time distributions and advanced quantities like response time percentiles. Lastly, because Line is available within MATLAB, which features through its optimization toolbox a set of optimization algorithms, like, for example, fmin-con or genetic algorithms, it is possible to combine these techniques with Line to optimize a performance metric over a space of possible models. This concludes my presentation, and I point you to the Line website for more details.